When you picture ice, you likely imagine snowflakes, glaciers, or an icy lake on Earth. But the universe is full of ice, and it doesn't behave the way Earth's ice does. In the frigid vacuum of space, ice can form from many different substances and often freezes into a disordered solid rather than the neat, crystalline ice we know. In fact, scientists at UCL and Cambridge recently discovered that cosmic ice isn't the uniformly amorphous mass we once thought. It can contain tiny nanocrystals hidden in its structure. Why does space ice differ so much from ordinary ice on Earth? In this deep dive, we'll explore how space conditions twist ice into strange forms, why that matters for everything from comet tails to the origin of life, and what spacecraft have taught us about this icy frontier. The Mendenhall Glacier in Alaska, false color satellite image. Earth's ice, here in bright blue, forms massive, crystalline glaciers under pressure and modest cold. Earth's ice, from winter's snowflakes to polar glaciers, has a highly ordered crystalline structure. Under Earth's atmosphere, 1 atom per pressure, 0 degrees Celsius freezing point, liquid water freezes into ice, familiar hexagonal lattice visible in snowflake symmetry. As Dr. Christoph Saltzman of UCL notes, ice on Earth is a cosmological curiosity because our relatively warm temperatures allow this perfect ordering. Deep glaciers pile up under gravity, compacting over centuries into dense, translucent ice. In short, terrestrial ice is almost entirely H2O with only tiny amounts of dust, air, or minerals trapped, and it forms by freezing liquid water. Yet beyond Earth, ice takes on many forms. In the outer solar system and interstellar space, ice can be made of CO2, methane, ammonia, NH3, nitrogen, N2, and other volatiles, often mixed with dust or organics. For example, Pluto's surface is coated with frozen nitrogen and methane, while mountains there are actually built from water ice bedrock. Titan has lakes of liquid methane, and Jupiter's moon Europa and Saturn's moon Enceladus are cloaked in water ice but speckled with salts and organic compounds. Comets are literally dirty snowballs, blobs of water ice mixed with frozen CO2, ammonia, methane, and rock dust. In short, space ice isn't just H2O, it's a cocktail of ices, each freezing out under ultra-cold conditions. Icy mountains on Pluto, photographed by New Horizons, while dark basins are frozen nitrogen and methane. This shows that on other worlds, ice can be exotic and surprisingly strong. Composition. On Earth, ice is essentially pure water, H2O, ice. In space, ice often contains other frozen gases, CO2, CH3, NH3, N2, etc., mixed in, depending on the environment. Molecular structure. Earth's ice, IH, is crystalline, hexagonal lattice. Space ice typically forms as amorphous ice, a disordered glassy solid, because the ultra-low temperatures prevent molecules from arranging neatly. Recent lab studies even show space ice can contain tiny nanocrystals, 3 nanometers wide, embedded in this amorphous matrix. Formation. Earth ice forms by freezing liquid water, rain, snow, lake freeze, etc. In space, ice often forms directly from vapor via deposition in a near vacuum, or by rapid freezing of plumes. For instance, water vapor jets on Enceladus condense into ice particles in the moon's frigid atmosphere, and interstellar dust grains act as nucleation sites in molecular clouds. Environment. Earth's ice forms under atmospheric pressure and gravity. Space ice forms in a vacuum and microgravity with temperatures hundreds of degrees below zero. With no pressure to compress it, space ice can be extremely porous and fluffy, quite unlike Earth's dense glacier ice. Behavior on Earth. Ice melts at 0 degrees Celsius at 1 atomer and participates in a water cycle. In space, there is no liquid phase. Warmed ice sublimates directly into vapor. When comets approach the sun, their ices vaporize and stream into characteristic tails rather than forming puddles. Understanding these differences is crucial for interpreting planetary science and astronomy. For example, the James Webb Space Telescope has detected complex ices in interstellar clouds, confirming that molecular ices like CO, CO2, CH3OH, NH3 coat dust grains where stars form. Spacecraft like Cassini and Galileo have flown through icy plumes and crisscrossed frozen moons, analyzing the ice composition. All of this shows that space ice is less like Earth's crystalline ice and more like a cosmic cocktail, often glass-like and mixed with other volatiles. Understanding ice in space also has big implications. Water ice is a potential resource for future exploration, e.g. lunar polar ice for drinking water or fuel, and it holds clues to life's origins. One famous idea is panspermia, that comets brought life's building blocks to Earth. But the new finding that much interstellar ice is partly crystalline means there's actually less room for trapping organic molecules. In a partly crystalline ice, tiny gaps close up, so amino acids and other organics would be less well preserved. This may slightly complicate the idea that Earth's life ingredients were delivered in space ice. Yet crucially, those dirty snowballs still contain organic ices, methanol, ammonia, etc., that mix with water in complex ways, helping seed planets with chemicals. Ice isn't just a curiosity, it's a record of conditions in the cosmos. The structure of space ice can reveal temperature history, radiation exposure, and chemical evolution of its environment. For instance, detecting amorphous versus crystalline ice on Europa's surface could tell us about how much sunlight or Jupiter's heat has processed it. Likewise, ice on Mars, water and dry ice, encodes climate cycles, and the bright icy surfaces of moons like Enceladus affect their thermal balance. Space agencies plan missions, Europa Clipper, lunar landers, comet sample return, partly to study these ices. And with water ice as a vital resource for habitats or fuel in space, knowing its form, powdery, solid, pure, or mixed with other ices, is essential. In summary, space ice and Earth ice share the same basic ingredient, H2O, but little else. Earth's ice forms in a thick atmosphere and always crystallizes neatly. In contrast, ice in the void of space can be amorphous, mixed with exotic frozen gases, and structured in surprising ways, as new experiments confirm. Next time you see icebergs or winter frost, remember, out there in the cosmos, ice is a far wilder thing. Scientists continue to probe these icy mysteries because every frozen grain in space is a clue to the story of planets, comets, and perhaps life itself.